All right, so we have continued fractions. We can calculate them using the algorithm from the last lecture. If we stop after finitely many steps, we'll get a special fraction that I'm calling a convergent. Convergents are special because convergence will approach alpha as n goes to infinity. So a bigger n, this fraction will be closer to alpha. There are two things we got to worry about to actually make that something that's useful to us. Number one, I want an estimate for how good this convergent is. And number two, I want to be able to actually calculate the numbers Pn and Qn. So far, all I've been doing is saying, we'll do our continued fractions algorithm, right? Get the integer part, subtract it off, take a reciprocal, get the integer part, subtract it off, take the reciprocal, and that's great and all. We can calculate the integers, those ANs that go into the continued fraction formula, but I want a quick way to actually calculate Pn and Qn without going batty. So last lecture we saw some of the convergence to pi. The first one is 3. The next convergent is 22 on 7. The next convergent after that is 333 on 106. The next convergent after that is 355 on 113. And these fractions we saw are getting ever closer to pi. So how good is this approximation? Here is a lemma. And again, I won't be proving this one today because I'm saving my only proof today for the last chunk of the lecture. If alpha is any real number, and Pn and Qn is the nth convergence to alpha, then the difference between alpha and Pn on Qn is less than or equal to 1 divided by the product Qn and Qn plus 1. So I'm using the absolute value bars here for technical reasons. This difference could be positive or negative. But just in terms of magnitude, how close these two numbers are depends on, 1, what's the denominator that I've presently got, my Qn, and 2, what is the denominator I would have for the next convergent. So in the example of pi is close to the convergent 22 on 7, the lemma tells me that this difference here is less than or equal to 1 divided by 7 times 106 as my denominator. 106 was the denominator of the next convergent. And so this difference is going to be less than 0.0013 and so on. So that's good. That tells me that how good this approximation is, I can figure it out in terms of my present denominator, but also this next denominator that I may or may not have after n many steps. This, by the way, is the reason why the convergents actually tend towards alpha in the limit, because as n goes to infinity, the right-hand side of this inequality goes to 0. So this difference has to go to 0, and that's exactly what I'm looking for limiting behavior, if you've done calculus. So ultimately, I want to have a formula to calculate my denominator Qn, and that should also help me get my Qn plus 1, so I can make that estimate a little bit easier to manage. How do I calculate the convergence to some real number? Well, I'm not going to get around needing the actual integers a0, a1, a2, and the rest. I'm just going to need to do that, so somewhere in here I'm going to be doing the continued fraction algorithm. For right now, since I already talked about the algorithm last time, for right now, let's say I have these numbers up to, an, and I know that my Pn and Qn is just the simplified version of this formula, this fraction here. If I knew my an plus 1, right, the next integer in my lineup, how do I get my next denominator? And here is the formula to use. And a typo. Get that fixed. The convergence to some alpha, right? Alpha is a real number. Its infinite continued fraction expansion is this. A0, A1, A2 are just the numbers that pop out of using the continued fraction algorithm. How do I get the numerators and denominators? My Pn will be An, this is my number from up here, times my previous numerator, Pn minus 1, plus my previous numerator, Pn minus 2. My denominator Qn will be An, the same An as before, times my previous denominator Qn minus 1, plus my previous denominator Qn minus 2. So this is a recursive formula. If you know the last bunch of denominators and you know the next a, you've got the next numerator and denominator. And of course, I have to start somewhere, so my P0 has got to be this A0, my Q0 has got to be 1. So this is the recursive formula for just directly calculating the numerators and denominators, Pn and Qn. Now this is a formula I will be proving, and that will be the final chunk of this lecture. See you soon.